Alright, quite honestly, the best part about logic and truth tables is that you get to use laws of logic. In order to use laws of logic, you have to know some, well, in order to do the proofs, you have to know the laws of logic. And so I have come here to help you. And what I'm going to do is I'm just going to hop on in. If I have P or Q, and that's true, and I know not P, three dots means therefore Q must be true. And this is the law of disjunctive inference. Um, and the reason why is because in P or Q, they're true basically whenever they're both, one of them's true, but this says that P is false, well not P is true, which means that P must be false, therefore Q must be true. And similarly, if Q was false, then P would be true. So that's disjunctive inference. If we're working with conjunctions, I can say if I have P is true and I have Q is true, I can therefore say that P and Q is true, and that's a conjunction. I suppose you could probably call it conjunctive inference. I'm not going to say that because I'm not 100% sure. But similarly, if I had P and Q, I could therefore just say, oops, I could therefore just say P is true. Or I could say if I have P and Q, therefore just Q. And the reason why is because look, the only time P and Q is true is when they're both true. I'm not sure what this is actually called, which is not good, but I'm going to call it the law of conjunction, and you're going to have to imagine that you can read that word, and this is conjunction, and that's okay. So there's a few more. There's one that's really wild, but we're not going to get to it yet. We're going to get to modus ponens, which is if I have P implies Q, and I have P is true, well, take a look. P implies Q. Oh, wait a second, there's a mistake here. Yowzas. Must be true. It says P implies Q. If P is true, then Q must be true, because if Q is false, then it would be false. So, then Q, and that is modus ponens, which, according to Wikipedia, means the mode that affirms. Modus tollens is if P implies Q, and we have not Q, that means not Q is true, which means Q is false. Well, that means that therefore P must be false. Because, take a look, if Q is false and P is true, then you get false. So if Q is false, then P has to be false. And that's modus tollens, or tollens, and that means the mode that denies. I'm going to do one that's, this is one of my favorites. We have P implies Q, and I have Q implies R, therefore P implies R, and this is a chain rule. This is actually one of my favorite ones of all time. If I had to make a top 5 list of my favorite laws of logic, that'd be right up there. Here comes one that's super wild, and it's actually a kind of cool one to prove. I'm not going to prove it, but you can if you're bored. And it's called De Morgan's Law. All right, so you might want to get this down. De Morgan's Law, and there's two of them. And it says basically if I have not P and Q, that is true if and only if if you can use your powers of imagination, double arrow, if and only if not P or not Q. And similarly, if I have not, and then the grouping P or Q, that's true if and only if not P and not Q. Is that wild? And that's it. Those are pretty much the only laws that we're going to do. There is another group, and it's inverse, the converse, and the contrapositive. And here's what you need to know about these. The inverse and the converse aren't always true. The inverse means instantly negate. So that becomes not P implies not Q. But P implies Q and not P implies not Q is not always true. Alright? Not always true. Converse is change the order. So if I have if P then Q, P implies Q, you change the order and that's Q implies P. And that's not always true. But here's the weird thing. This one, which one of my former students like to call the most opposite thing ever, says if you have P implies Q, I just want to make sure that you guys know that this is not an operator here. This is all I'm working with. P implies Q, and you get not Q implies not P. These two, P implies Q, is logically equivalent to not Q implies not P. Alright, in any event, this was video 2. I wanted to make this because we're going to be doing 2 proofs, and that's it. I hope you enjoyed it.